Hi everyone. Okay, we're about to start part 2 of our dynamic stability during GAIT slides. So if you remember the week that James Christensen came in, I had assigned you guys to read this paper, and our goal was to take it up as a journal club style discussion. That's not possible, so I'm going to try to facilitate that using this form, so bear with me. So first off, this study was looking at a quantitative gait analysis in Parkinson's disease. And I'm going to primarily highlight on their findings as it pertains to the power analysis that they did. But we'll talk a little bit about the spatial temporal patterns too. So hopefully you had a chance to read it. If you haven't, stop this video, go back, read the paper, and then look at this, because I think you'll get more out of these lecture slides. Okay, with that said, the objective of the work was to compare gait parameters in Parkinson's disease during the on phase of the medication cycle compared to those healthy elderly control participants. So I wanted to initially have a discussion about why the on phase of the medication cycle. Why do you think that might be important to think about? Any ideas? Joking. Okay, it's possibly because the researchers really wanted to get individuals at their sort of at their best capacity in terms of their mobility and movement, and that's perhaps where, if we're going to have some type of intervention or some type of rehabilitation program, that's where we want people to be at their optimum before we ask them to do things in that rehabilitation setting. So that's, I think, one of the reasons why they chose to do that. Okay. They had 15 individuals with Parkinson's disease, and they had 9 healthy elderly controls. Just to note that they weren't exactly age and gender matched, and more on that in a little bit. Okay, and clearly not an equal sample size either. Okay, the main outcome measures, they looked at spatial temporal components of gait, kinematics, as well as kinetic gait parameters. And one of the things that they were really curious to look at was what was the underlying cause or mechanism behind the reduction of stride length, because they felt that this is one of the most prominent features of Parkinsonian gait. So often individuals with Parkinson's disease walk with a lower walking speed, have a longer double support phase, and reduced stride length. So really they were curious about this component and what was causing that. So that's why they went to a power analysis. Okay, first off, just wanted to draw your attention to Table 1 characteristics. So this is the Parkinson's group and the control group statistics data. And this is sex, age, weight, and height. And this is the t-test, although I will note that for this particular t-test, it was a chi-square. Of course, it's sex, so it makes sense that they actually use a chi-square because that's a non-parametric statistic. And they used a 95th% confidence interval, so we're looking for differences of less than 0.05. So it was trending perhaps here for this, and that makes sense because they had they had an unequal sample size for sure, and they only had 4 women, 6 women in the controls, 11 and 3. So clearly that was trending towards being statistically different from each other. But for the other demographics, age, height, and weight, the 2 population groups were comparable, or not significantly different at the very least. So now, if we were in class, I'd ask for your thoughts on the spatial temporal variables of gait. So just wanted to draw your attention to the fact that they flipped up the columns here. Don't know why, but they flipped it from, now this is the control in the first column and the PD group in the second. So just wanted to draw your attention to that. And there's your statistical analysis right here on the other side. P-values of less than 0.05, so 95th% confidence interval is what they looked at for statistical significance, and the means that are reported are there, as well as the standard deviations. Okay, so first off, when I look at this, it's pretty clear to me that the walking velocity between the control group and the PD group was significantly different statistically as well. It's like 1.2 compared to 1.94. So they significantly walk slower than their healthy control group. And because this is such a reduction in gait velocity, it's within that range of a high risk of fall. So that's, I think, one of the first things that's apparent. Secondly, if you look at the stride length characteristics here, clearly stride length is a component of walking velocity, and you can see that that's the case for sure for the Parkinsonian group. It's 1.03 compared to 1.2, so it's about a 20 centimeter reduction in stride length on average, and that is also statistically different between the two groups. And if you look at the cadence, double support, and single support phases, however, they were not statistically different, perhaps trending for that single support, but less or greater than that 0.05. So they have reported that the cadence and single double support phases were not directly affected by Parkinson's disease, which perhaps was something they weren't expecting. So that was an interesting finding. Okay. They also found that there was no relationship between stride length, gait velocity, and ankle and hip power generation. So they also did some correlation analysis, and I'll get to those in a second. So now I went through and actually just pulled out some figures in the next few slides just for discussion amongst ourselves. So I'll lead that discussion. So this is the joint angular excursions at the ankle, knee, and the hip and pelvis. So just to orient you to these slides, this is the ankle here, the knee, hip, and pelvis. And this is a percentage of the gait cycle. Obviously, 60% is where you're moving from stance into the swing phase. So that's what's noted by this dark blue line here. The control group is on average is demonstrated by the dotted line, and then the plus minus standard deviation is depicted by the gray bars that are surrounding that dotted line, and the PD group mean as represented by the thick solid line here for any of the next couple of figures. Okay, first off, what do you see in the data? Well, first off, I see that the PD group has a reduction in that ankle dorsiflexion component right here. You also see no significant differences, so those solid line is well within the gray bounds of the plus minus standard deviation of the control group. Similar finding for the hip flexion extension. There is a slight reduction in the pelvis rotation, and that's more apparent here just as they're moving from stance into swing. So they concluded that there was a reduced joint angular excursion at the ankle, but not at the hip or the knee joints, and that the pelvic rotation was higher in the PD group, but it wasn't actually statistically different. I think just because it was just a slight increase here, just at that one particular point. So that was what was happening at the joint angles. In terms of the ankle, knee, and the hip moments, so remember, this is really important for us to know to be able to calculate power of what's happening here. So just to orient it to these graphs, this is the moment along the y-axis. Along the x, this is a percentage of the gait cycle. Remember, this is going to be the moments that are calculated from the force plate, so we can only calculate that during the stance phase and obviously during the swing. We don't have a foot on the force plate, so we can't calculate moment. So plantar flexion, dorsiflexion for the ankle, for the knee extension, flexion, and hip extension and flexion as well. So what do we see? So first off, we see a reduction in the ankle moment at that really important phase just before toe off, which if you remember from part 1 lecture, that's a really important phase of the gait cycle where 2/3 of our power come at this big power burst generation. That's part of that ankle moment. So a reduction in that ankle moment. In the knee, we also see a reduction in the knee moment compared to the average of the control group. And the hip, we also see a reduction in that hip moment as well in terms of hip extension. So you see these different components. So the reduced ankle moment, plantar flexion was decreased in the PD group, and this was perhaps in part due to that range of motion that we just discussed on the previous slide, and that push off or that toe off phase of the gait cycle. Okay, we also see reduced knee moment at about 40% of the stance cycle, and a reduced hip moment at about 50% of the stance cycle. So we see these, all three moments are being reduced here. Okay, what's happening at power? So if you remember, this particular paper did not report the angular velocities, they just report joint range of motion and moments, but you can sort of infer that angular velocity if you look at the slope of the joint movements from the very first series of graphs. And then based on, obviously, net joint moment, as well as our angular velocity, we can calculate ankle power. Calculate our powers at the ankle, knee, and the hip. All right, so what are they seeing? First off, they're seeing a reduction in that ankle power, which probably comes as no surprise because you're seeing reductions in the joint angle, and you're also seeing reductions in that moment at that around that phase of the gait cycle. You're also seeing higher variability here for the knee power. That was consistent across both groups actually, so a much larger standard deviation there, but definitely a reduction in the knee power. And the hip power, you're seeing periods where this is reduced as well within that Parkinsonian group. So in terms of the power generation, we see a reduced ankle plantar flexor power and variable knee power. We also see reduced power at the hip. Once again, I didn't demonstrate that here, but if you go to that paper, go back to the paper that I'm sure you've all read, you'll see that they report no relationship between stride length, gait velocity, ankle, and hip power generation. So what is the cause of this slower gait in subjects with Parkinson's? Like, what's the mechanism behind it? They proposed that it was reduced ankle moment. That was really important. Obviously, that's factored into, or that's heavily influenced by the fact that they have a reduced range of motion at push-off and a reduced hip power absorption as well. And you can see that again in this particular slide right here. So what were the big take-home messages from this paper? So in conclusion, they found that the plantar flexors were the most affected in Parkinsonian gait, but hip flexors were also implicated in those abnormal gait patterns. That walking velocity did not largely affect the results. It wasn't the cause of the kinetic deviations, but rather those plantar flexor movement powers were actually what was resulting in some of the changes in those walking velocities. They also found no correlation between stride length, gait velocity, and power generation. So it suggests that perhaps central and peripheral factors are involved. So central makes sense because that's the Parkinson's obviously results because of a lack of dopamine generation within the basal ganglia. So it makes sense that that's how they would conclude for this particular study. All right, so hopefully you got a little bit something out of how we can use those power curves within trying to understand pathological gait. And I also want to just get you guys to think about coming full circle to part one of the lecture series. Part one, of course, was where we discussed that really neat, innovative study where they were using biofeedback training in young adults. To see if they could actually use that screen placed in front of a treadmill to increase that power generation coming from the ankle plantar flexors. So although this particular paper from Swafwa was published in 2005, hopefully some of those new recent technologies that are out there can be used to improve power in individuals with Parkinson's disease. And that might be a really neat and innovative rehabilitation strategy in the future that can improve gait. The mechanics of gait in those individuals. So just wanted to get you guys to think back to that first part of the presentation. Okay. Finally, just in conclusion of this whole series, part one and part two, I want you to consider the control of gait, and I want you to think, reflecting back upon human-like robots and how the number of engineers and the years that have gone into the design of these really cool robots and what they can do. It's pretty impressive. But then I want you to check out this web page from YouTube from Boston Dynamics down in the States. It's pretty cool. It's pretty neat research. But then I want you to contrast that with this link, which is from Denmark's Forest Kindergartens. It's a really cool program, and I want you just to take a look, specifically at section 2.15 and then 4 minutes 50 seconds in to this little clip, this video clip. And I want you to think about it. In Denmark, they're actually trying to advocate for kids going outside and doing outdoor learning, which I'm doing with my children right now. This sort of takes it to the extreme, but it's pretty cool. And I want you to, at these 2 points, you'll see kids doing some really amazing things. And I want you just to think about the fact that there's no engineers behind them sort of controlling or writing software or making sure that spring damper coefficients are working. It's just kids saying, hey, I want to climb up that tree, and figuring out how to do it. So I do think that we can learn a lot just by watching kids or individuals with different pathologies. We can understand what's happening with them if we sort of sit back and take sort of a different viewpoint. So it's a pretty cool video. I hope that you it causes you to stop and think about how we move and work through the space, and how challenging it is for individuals that are trying to design robots, like how many different things they have to control and adapt and think about when they're trying to design these robots, which makes them all the more impressive. Anyway, I hope that this series was interesting, and I hope everybody stays well. And yeah, more soon. We'll talk to you soon. Bye.